All right. So just really quickly, a couple of logistical things. First of all, I usually put up a holiday that is today, but yesterday was a national holiday that I wanted to celebrate and acknowledge for you all as well. And that is Transgender Day of Visibility. And it's one of those things that I think sometimes as a person who doesn't identify as transgender, you're like, oh, that's not about me. But it's one of those things that you will certainly, if you have not yet, encounter someone who is transgender in your life, right? And I just want to remind you to show kindness, right? To show love. Everybody's a good person, right? We have to assume positive intention. So be supportive of the people around you. Or if you are ever questioning or need anything, know that you are loved by everybody in here and everybody around, right? That is what we do. All right, so that's my little PSA for the day. Share love. That's our goal, right? I've got a few physicsy things to start off with. On Friday, we were talking about the Andromeda Galaxy. I told you that the Andromeda Galaxy is going to collide with the Milky Way Galaxy, and I found a little clip to show you what that's going to look like, right? Obviously, it's not footage of it because it hasn't happened yet, but we're going to take a look at that really quickly. I've got quizzes to give back, and then we're going to do a bunch of stuff. It's going to be a really good day. Today is a good day for physics. So it's going to be good. Can you hit the lights for me, Sam? Awesome. So we're going to pull this up here. This is, hopefully there is no ad. Is there an ad? Oh, there's always an ad. All right. Ad. Skip ad. All right, friends. So here we go. Just a couple minutes, not a long one today. Oops, is it going? What's that? Oh, I don't know. I've never really wondered about that, to be honest. No, this isn't going.
What's our next quiz?
We'll talk about it in a minute. All right, here we go. "68 miles per second. We're getting closer and closer.
Wait, 68.
Do you want me to go back to that?
Yeah.
Okay, hold on. Back up. Hold on. Pause. Okay.
That's crazy.
What's wrong?
Will we get exploded?
Well, just watch. Just be patient, friends. Yes. So we are moving toward the Andromeda Galaxy. So you can see Andromeda. I mentioned this to you before. Naked eye, not in Iowa City, but
So
you
like
go
in
out.
like the forest.
Well, if you were in the forest, then there would be trees usually.
Okay, so
But like if you go out to a rural area, right? So
Yeah.
yes. If you go to a rural area, then yes, you would be able to see it.
Yes. That'd be great.
Yeah. So there is a really great app on your phone if you've never, if you are interested in this. I think it's called Night Sky, and it's a really cool app where you can like pull it out. Don't get it out right now, but you can pull it out, and then you can like point it at a part of the sky, and it will tell you what is there, right? So it'll tell you what the planets or the stars are. So if that's something that's interesting to you, it's like a free app because I don't pay for apps usually, but so it just tells you what it is, and so you can like search like where's Andromeda. Not always up, but often. And so you can take a look at it. And you'll notice, so these are simulations of what the sky looks like. This right here is the Milky Way Galaxy. I think I've told you guys before that if you go out in the night, at night, again, farther, not in North Liberty, not in Iowa City, but if you drive out so that it's really dark, okay, you can see the Milky Way. It's just a brighter band of stars that kind of goes right above our head. Okay. And that is because our galaxy looks a lot like Andromeda. It's a spiral galaxy, and we are looking out at that band. Does that make sense? So that's what we're looking at. So these are simulated pictures of what it's going to look like. So this says 2 billion years from now, this is what the sky will look like. So if you remember from before earlier, this was smaller, right? And it's going to get bigger and bigger and closer and closer. There it goes. So here's the simulation. So again, this is starting 3.75 billion years in the future. So to be clear, you will not be on Earth, right? To be clear, probably the humans will not be around, Okay. We don't know exactly when our sun is going to go boom. Okay. So our sun may not even be around, right? Or well, not in the state that it's in, depending. So just, but it's kind of interesting. Every second, 1 million years will go by. Just like mentally get that in your brain because that's weird. There we go. 1,000, that's a million years. You with me there? It's a long time from now. So again, these are spiral galaxies. I'm going to pause this for just a second before anything happens. So this is Andromeda. So this is looking very similar to the poster up there, right? It's a spiral galaxy with a black hole at the middle, okay? And this is the Milky Way galaxy. We are about 2/3 of the way out on one of the spiral arms. Does that make sense? Like our sun exists, and so therefore we exist like here-ish, right? Somewhere around there, just so you've got kind of a mental image of what's going on. Again, every second is a million years here. Okay, so this is interesting. It says the solar system is going to survive this. And I think I mentioned this to you on Friday as well. I can't remember for sure. But the amazing thing, as these two galaxies, again, with billions of stars, collide, there is very, very low probability that any two objects with mass are actually going to hit. Okay? Because there's so much space in between objects that it's just going to kind of like come together like this, and they're going to kind of move around each other, right? Remember that every two objects with mass are going to interact, right? So there's going to be all kinds of interesting things, which is why all of this swooshiness happens. But our sun...
So nothing bad's happening.
What's that?
Nothing bad is like happening.
I mean, I guess it depends on what you consider bad. But, it's just a bunch of gravitational forces that are... And it said new stars are forming. You have to remember that new stars are forming all the time, right? That is true everywhere. But yes, but Earth is no longer habitable. Like, we will not be here to see this. We may be somewhere else if we can get our act together, but we won't be on Earth. Yeah.
Will the centers collide?
Yes, and so we're just going to keep watching because we got a couple more seconds. Yeah. So at the center of each of those galaxies, a black hole, a supermassive black hole. Yeah. Oh, is this the beginning again? No. This is still going. Okay, I was going to say. So there you go. Yes, so they're all going to collide. They're all going, not all, but like lots of different ones are going to interact, right? So it's just kind of interesting and weird, right? But all of that happens just because of like the physics that we understand, we know and we love. There's some questions out there about what's going on with dark matter and dark energy, if you've heard those terms before. So there are still outstanding questions, but all of that is based on what we know with the physics that basically that you guys have gone through already. So it's kind of cool. Any other questions about that before we move on? I mean, there are lots of questions out there, but all right, I'm going to pause this for a second and give you guys some quizzes back. For EM spectrum notes, we started this on Friday. Your EM spectrum sheet has this on the bottom. We're going to build it again. I think we may have started the conversation on Friday, but I want to start it again because I want to make sure that it's a good conversation, a strong conversation. Okay. We ready? Yay! All right, so I think that we had some labels done up in these boxes already. And in these boxes here. So I'm going to add a few things and we're going to look at a few things because, friends, I want to make sure that you really understand this and you internalize it. It's not just a memorization game. Okay? So I'm going to start with the wavelength because the wavelength is really easy to see on the picture, right? Remember, wavelength is measured crest to crest. And so if we look here, the wavelength is changing, but you can really see, come on, silly thing, that the wavelength here is a lot bigger than the wavelength here, right? Yeah, so the wavelength here is large or long or big. And the wavelength over here is small, little, tiny, yep. Okay. So the waves that have these big wavelengths and the waves that have these small wavelengths, which ones move faster? They all move the same speed, right? Right? Not a trick question, but a thinking question. That's what we're doing here, right? The electromagnetic, this just means light. And these all move at the same speed. The speed of light, right? With the speed of light, we have talked about the value of it. It's 3 times 10 to the 8th meters per second in a vacuum. And sometimes, because we get tired of writing 3 times 10 to the 8th meters per second, because that's a lot of graphite to use or a lot of ink to use, sometimes we'll just call that this nice, easy little constant. And the constant that we use is the letter C. Okay, so C is the letter we use for the speed of light. You may have known that without actually knowing it because you've seen this equation before, right? E equals mc squared. The C in E equals mc squared. The C is the speed of light. Okay, so you've seen that before, perhaps, just somewhere. And so I just wanted to show you that. And we'll talk about that, like what all that means later. But I just wanted to tell you that you've seen that. But if you see the letter C, that's what we're talking about. It's a little c. Okay, so if they're all moving at the same speed, and we know that the velocity of a wave is equal to the frequency times the wavelength, then without really having to do a lot of thinking, if the velocity is the same and we have a really, really, really big wavelength, what does that mean about the frequency? It's really, really, really small or low, right? Okay, so these are low frequency waves. And on the other side then, they've got to be high frequency. Which also kind of makes sense if you think about it in terms of time, right? We got these waves go boom, 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 as opposed to boom, 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 right? One other thing that you might want to make a note of is that frequency, the relative size of the frequency also dictates how much energy a wave has. So low frequency also means low energy. And high frequency waves also have high energy, which is kind of a nice thing to know, especially as we kind of go down here and talk about different types of waves. All right, so we've got generally 7 different categories of waves that we talk about in the electromagnetic spectrum. To be clear, they are all part of light, right? So when I talk about light waves, I'm talking about all of them, not just red, orange, yellow, green, blue, indigo, violet, okay? All of them. The biggest wavelength waves we have are what kind of waves? They are radio waves. Radio waves have wavelengths on the order of a size of a football field, okay? They are big, from crest to crest. Think order of the football field, okay? Like that's how big they are. Huge, okay? Big, 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 big waves. What are some examples of radio waves? Did you write those down? Did you get some of those figured out from your from your notes or from the book that you were looking at? TV, yeah. TV waves. What else? AM, FM. What else? Anything else? A lot of communication uses radio waves. The biggest misconception with radio waves is that people think that radio waves are sound waves, right? Because when you turn your radio on, you get sound. But radio waves are light waves. The reason we talk about them that way is that if you're tuning your radio, and I know we don't listen to radios all that often anymore, but maybe you listen to radio in the car now and then. When you tune your radio, you are tuning it to get a specific frequency of radio waves that are out there in the world. If radio waves were sound waves, it would be really, really, really loud. Because all of the radio frequencies that are traveling all over, like they are all over all the time, okay? But when you tune your radio, you're setting your radio to pick up a certain frequency, okay? And that frequency is associated with a certain thing that then is going to translate into a sound wave using the speaker. Does that kind of make sense? Okay. So that's what a radio wave is. A radio wave is not a sound wave, it is a light wave. It moves at the speed of light at 3 times 10 to the 8th meters per second. Just like every other kind of light. Next biggest. What is it? Microwaves. Yeah. What are some examples or some uses of microwaves?
A microwave.
A microwave, right? I'm going to put in parentheses appliance. And then you might want to write down just that we remember now that a microwave, the appliance, why do we use our microwaves? Why does it use microwaves? Do you remember we talked about this on Friday?
The water.
It moves the water.
It resonates.
It resonates those water molecules because the microwave frequency is the same as the what of water?
Natural frequency.
Natural frequency, you got it. Yep. So microwaves specifically, what was it? 25 or 2450 or whatever. Okay. The frequency is the same as the natural frequency of water. So that's kind of interesting. Okay. Microwaves are also used a lot for communication. Okay, there are a lot of communication satellites and a lot of communication things that use things in the radio or in the microwave, and there's not like a specific cutoff. It's not like you have a fundamentally different wave if it's a radio wave versus a microwave, because it's a big spectrum. We just kind of arbitrarily cut them off at different places because we use them for different things generally. Yeah?
Why do they call it a microwave if the wavelength is longer?
Well, it's smaller than a radio wave. I mean, I don't know where the etymology of it comes from. You could look it up. I'm sure that somebody has written about it, but I don't know for sure. I just know that, it's smaller than a radio wave. What does it say over here? I don't keep track of these things. So we're talking on the order of 3 centimeters. So the wavelength is about this big, crest to crest. Okay. So we're going from football fields, right? And not all radio waves are football field size. Some of them are about human size. Okay. Some of them are a little bit, 30 centimeters. But when you get to about 3 centimeters, that's when we're talking about microwaves. That's kind of where the cutoff happens. Okay? Again, I'm going to write here communication because we absolutely use them for communication. And Josie, I want you to remind me when we get over here a little bit to come back to address the concern that your dad had with the microwave. Does that make sense? Mm-hmm. Yeah. Because it'll make more sense when we're over here. Okay, so microwave, what's the next one? Infrared. So infrared waves. Sometimes we write this as IR. You may have seen that, so I just want to throw that in there as well. When do we use infrared? Or when have you seen infrared? Or when has it come up in conversation or life? Do you know?
See, the military uses
Say that again.
they look for heat signatures.
Why did I write
Mm-hmm.
Oh yeah, and then they light up.
why?
Dark.
Yep, and we'll talk about that in a second. What's that?
Dark.
Yep, so darkroom often we'll just use like red or sometimes IR. Yep.
Isn't that where they used to produce images?
Yep. So prior to digital photography, when you used to use negatives to actually you'd expose the negative and then you would have to use that to print a picture, right? it's really fun if you ever get an opportunity to do like real photography and actually get to develop your own pictures. Super fun. Take advantage of it because it's interesting how it works. But anyway, in the darkroom, you can't have visible light because otherwise, or you can't have like high energy because that will expose the, yeah. They dip it in exposure chemicals. Mm-hmm. Yep. So like, say if you watch like spy movies from like the 70s and 80s, yeah, like they're like, you know, they've got, yeah, like that's what they're talking about. And that's how all pictures used to be developed, believe it or not, you know, before what, like 2000, like it hasn't been that long. But anyway, yeah. So dark rooms, they use this stuff as well. Yeah, absolutely. Any other things that you know about infrared? The signal that I use here, the signal that you use when you're sitting at home, okay? The signal that you use when you're doing any sort of remote control thing, okay, uses an infrared signal as well. Yeah. And we also use this for communication. Oh. Okay. And we're going to come back to IR and talk about it a little bit more in just a minute too. So we will revisit a couple of those. And then we've got visible light. So when you go home and your parent says, hey, what did you study in physics today? Because I'm sure that's how the conversation goes. Or maybe it's, what did you do in school today? And you're like, oh, I'm talking about my favorite class, that was physics. And in physics today, we talked about light. Your family members are going to be like, oh, well, you just talked about the rainbow, right? Like you talked, right? Because that's what we often think of as light waves. Again, it's bigger than that. But the rainbow starts with what? Red. And the reason it's red is because it's on this part of the spectrum. You always remember, friends, that infrared, the next one after infrared is going to be the visible part, and it's going to be red, right? What comes next? Sing the song for me if you know a song. Yeah. So we're going to do this. So we got orange, and then we got yellow. My kids are like, they sing some weird song. That's a rainbow, blah, blah, blah. I don't know. They sing it a lot. It's kind of cute. I don't really know how it goes. Red, orange, yellow, green. Then what's next? Blue. And then what's next? Indigo. Whatever that means. I'll tell you the story in just a second. That's actually more violet, isn't it? There's violet. So I was hanging out with my older daughter while my younger daughter was finishing up her, I don't know, gymnastics or something. And we were talking about the rainbow, and we were talking about indigo and how the indigo is not in any of the songs that they sing. And I'm like, but indigo is great. So then I had to look it up. Like, why do we have indigo? Nobody talks about indigo, right? And when you think about like the primary colors of light, we'll get there soon, or the primary colors of pigment, right? What are the primary colors of pigment when you learned when you were in kindergarten? What do you got? Red, blue, yellow, and blue, right? Does that make sense? And then when you mix red and yellow, you get orange. When you mix yellow and blue, you get green. And then when you mix red and blue, you get purple. And this indigo is not in there, right? Because you got three primary colors, you got three secondary colors. Indigo is a tertiary color. And there are tertiary colors between all of these two. So like, what's up with that? Do you know who we can blame? Isaac Newton.
Are you joking?
I am not joking. It is Isaac Newton. I was like, what? Like, I know, right? Like, you know how much I love him, and I've got another thing to blame him for. I know. So I was reading these articles about how Isaac Newton, because he was the first person to like write about color, and he was the first person to like write all this stuff out. And not only was he like a pretty decent scientist, I told you he was kind of a jerk, but he was also really into like kind of supernatural stuff as well. And in supernatural understandings of things, there are lots of beliefs of like that 7 is like the perfect number.
My dad knows.
So you can't have just 6 colors because then the rainbow wouldn't be perfect and light wouldn't be perfect and then science isn't perfect, right? So you got to add a 7th color, right? And then there were all these other little bits and pieces that I don't remember all the details, but you can totally look it up. Like, why did Isaac Newton do this? And then I was looking at, because I never really teach indigo, but it's in the song and it's in Roy G. Biv, because otherwise it's going to be Roy G. Right? And that's not very exciting because you don't have the I. And so then, the guy's name is all messed up too. Thank you so much. And so, anyway, it's all Isaac Newton's fault. Okay? It basically said, we don't need indigo. Like, who needs it? Not us. But it's in there. And it said, so it's like, why do we still teach it? It's just because You know how teaching works, right? It's me teaching you, and somebody else taught me, and somebody else taught her, and da-da-da-da-da-da. And so it's just one of those things that's been passed down from generation to generation, and it's always been in the list. So when you become a physics teacher, I'm giving you permission not to teach indigo. You don't need it. When you become an art teacher, you're going to call it one of the tertiary colors, and then you can tell them the story of Isaac Newton, unless you want to just, talk about how Isaac Newton was just kind of a whatever. And yeah, so he kind of messed everything up. Like you can totally do that. But anyway, there you go. Fun story for the day. There you go. All right. Visible light. We're done with it. Now, I was going to write one other thing down. And that is just to kind of give you a sense of how big visible light is, because it's at the top of our chart as well. Visible light goes from, I'm going to write it down. I'm going to ask you to figure it out. So the visible light spectrum, visible that we can see, goes from about 380 nanometers to 740 nanometers. So my question for you and for you to figure out with your table mate right now is, which one is red? The 380 or the 740? Nanometers. So that's a measure of what?
Distance.
Kids like their frequency.
Wavelength.
Wavelength. So figure out which one is red and which one is blue.
Okay, so
You got this.
red is the 740 because it has a higher wavelength, which means it has less energy. Because violet.
You wrote it the opposite way to trick us.
No, I didn't. I wrote it this way because this is when you look it up, this is what it says. And I wanted you to think about it in terms of what does it mean for wavelength. So there was no tricking intended. It was a 50-50 shot, right?
I'd like to say that, but really it was like a...
It's a thinking opportunity. It's better for me to do that than to just tell you because you're not going to remember. This conversation now is stuck in your brain. You see what I'm saying? All right. What are you upset about? No.
But that doesn't make sense because blue is the base.
I mean, that's just like the indicator.
Yeah.
So I would say no, but like the chemists, they always rely on us, so maybe. I mean, I don't know. All right, so what did you decide for red? Is that the 740 or the 380? 740. So 740 nanometers, about, okay? And then 380 is our violet. Nano is times 10 to the negative 9th. So this is 740 times 10 to the negative 9th meters, which if we move that over, that's going to be what, 7.4 times 10 to the negative, 7th meters? That's a really, really small wavelength. So again, we're moving from radio, which is on the order of football fields long, okay, to the visible light that we can see is 7.4 times 10 to the negative 7th meters. It's very small. It's very small, right? Okay, and then 380 is even smaller than that. But also, if you think about that, this is really not a very big chunk of the spectrum. Okay, so just, reality check kind of thing. If you haven't yet written that down, is that what it asks in the thing right above where you've got it up there? What does it say? Oh, it says it by frequency. You have the ability to do this. So I'm going to let you do that real quick. Go grab a calculator if you need it. Okay, an opportunity for you. So again, nano is 10 to the negative 9th. And you know how fast light moves. So figure out what the frequency is of red light, what the frequency is of purple light, okay? We'll write them down here, and then you can also write them above in your chart. Make this quick, because we don't want to spend lots of time doing it, just a little bit.
You just do 7.4 times 10 to the 7th times x equals 3.
Is that mean nanometers?
So 740 nanometers. Nano is 10 to the 9th, negative 9th, excuse me.
So
10 to the
did you forget to put that?
Divide.
Where? Here?
No, that's in meters.
This is in meters, because instead of writing nano, I wrote 10 to the negative 9th.
What about the right side? That's also meters.
10 to the negative 7th in meters.
Oh, you said something right.
I just moved it over so you could get like a boom.
I got 4.
4.05 times 10 to the 14.
Oh, yeah.
For red.
For red, yes.
Red.
Yes. So again, once you've got those, are we okay? Is everybody understanding how to do this? And if the answer is no, then let me know. Want some help? Push it in the right direction. Let's do it. Okay, so I'm going to use this relationship right over here. You with me there? So I know the speed is 3 times 10 to the 8th. I know the wavelength, we'll do red, is 740 times 10 to the negative 9th. I'm looking for frequency, so I'm just going to solve this for frequency. So frequency is wavelength over speed. So again, for the red light, I've got 740 times 10 to the negative 9th meters divided by 3 times 10 to the 8th meters per second. I did that backwards, didn't I? I did. Sorry about that. Like, those units don't work. That's why we write units down. Hold on just a second. Let me write this down correctly so that I don't embarrass myself further. What'd you say, Ben?
I got it. I accidentally put 7.4.
Oh, that's going to mess you up, isn't it? Sorry about that, friends. 3 times 10 to the 8th meters per second. Units save the day. 740 times 10 to the negative 9th meters. So what are we getting for red?
4.15 times 10 to the 14.
Units are? Hertz. Yep, it's a frequency. And what did you get for blue or for purple?
7.89.
So we'll do 7.9 or 8 times 10 to the 14th as well. Purple. Okay. So you can go ahead and write those here. If you want to write them in your chart, that's great. And then the chart above. Okay. So that means that if you look at something that's red, light that is red that's coming, so like if you look over at my Cornell University pennant over there, the light that's coming off of that and going to your eye is moving with a frequency of 4 times 10 to the 14th hertz. 4 times 10 to the 14th oscillations every second. You with me there? If you look at the University of Dubuque one right next to it, it's moving at 7.9 times 10 to the 14th cycles every second. How does that compare with the frequency of sound, friends, that we can hear, audible sound?
The audible sound is a lot. It's a bigger range, right? No, it's a smaller range.
Yep, and they're also much, much smaller numbers, right?
Why?
Yeah. Right, because it's 10 to the 14th, so.
Oh, yeah.
Yeah, so it's big. It's a big range. All right, how we doing? We okay? Issues, questions, concerns there on visible light.
Wait, so.
Yeah.
Has there ever been a light that we can't see?
All of this light you can't see. And all of this light you can't see. The only light that we can see with our eyes is this stuff.
Yeah.
And that's what we think about, right? Because again, we're very, very self-important. But all of this and all of this, we miss a lot, which is why we have to think about things. And we'll talk about a little bit more of that in a second. Go.
So that means there's like a bunch of colors we can't see.
I mean, kind of, yes. So color is it's kind of like pitch. Do you remember we talked about pitch and how pitch and frequency are related? And pitch is what we perceive based on the frequency of light. So color is what we perceive based on the frequency of, pitch, sound, light, color. Right, you with me? Yeah? So you could say there are a bunch of colors, but it's not really color in the same way that we think about it, because all of the colors that exist, there are an infinite number of colors, right? Because you're aware that when you look at a rainbow, and we'll talk about how those work later, but when you look at a rainbow, it's not like there's a distinct red stripe and then orange stripe, unless you're looking at the rainbows that my daughters draw, right? That's got this stripe and then a stripe and then a stripe. But if you look at an actual rainbow, an actual thing that's produced, it's a spectrum. So there's an infinite number of colors in that spectrum, okay? But based on what you're asking, there are tons of colors or frequencies of light that exist here, and same on this in this direction. I'm gonna go here and then I'll come here. Go ahead. Yes, go. Yeah.
You had these things in chemistry last year.
Yeah.
And you look at the floor direction.
Yep. Yeah.
Line
And then
emission.
they
Yep.
give you
Yep.
a spectrum.
That's all here.
Yeah, but on the fluorescent ones, or maybe it was the other.
Fluorescent ones are a bunch of lines. Is that what you're asking about?
Yeah.
Mm-hmm. So we could talk about that a little bit more. We'll actually pull out the spectrum tube so we can look at them because it's really just physics. But anyway, basically what's happening is, I mean, I don't know how much you remember from chemistry or how deeply you go into chemistry. So like, if you think about, let's say, hydrogen. So you looked at the hydrogen tube, right? And the hydrogen tube has different energy levels. And so light is released when an excited electron goes from one energy level to another one. And it depends on which jump we're talking about, okay? The bigger the jump, the more energy it's losing. And the more energy it's losing, the further over this way it is. And so because hydrogen is quantized, right? It's got certain energy levels that exist. Then there are only certain jumps that happen.
So it's losing energy?
That the electron is losing energy, and that energy is leaving as a photon or as a particle of light that has a certain frequency, and that's what you see.
When they get, as you go left to right, when they get more energetic? Though?
These are more energetic. Yep. So we're losing more energy to the fall. We can talk about it more because it's pretty cool. Yeah. Yeah. Does that answer your question?
Yeah.
Okay. Okay. Other questions? All right. Let's keep going this way. It's got radio, micro, infrared, visible. What's next? Ultraviolet. Yeah. You guys okay?
Somebody told me a good joke.
You want to share it? Because I like to know good jokes.
No, it wasn't a joke. It was something we did. Something that was funny.
Are you okay?
Yeah.
Okay. Okay. All right. Ultraviolet UV examples. What do you know?
You said UV, sun.
I did.
Sun.
Yes.
It
Okay.
affects our skin and gives us sunburn.
That's what everybody thinks about, right? About light from the sun.
Is that wrong?
No, it's not wrong. But it's also kind of a misconception. So that's why I wanted to address it. So I'm glad you said that because somebody had to say it, right? So thank you. All right. So everybody thinks of the sun when you think of ultraviolet light, and that's good. That means that the PR campaign by the medical institutes has been very successful because they have trained you to think when I go out in the sun, I'm going to get a sunburn, and I'm going to get a sunburn because of the UV rays from the sun. That's absolutely true, right? So what do I need to do? I need to put sunscreen on my body, right? And if I don't put sunscreen on my body, then I'm going to get sunburn, then I'm going to get skin cancer, and then I'm going to get sick, right? That's what they've been telling you, and that's good because that means that you all wear sunscreen more often than I did when I was a kid, right? Okay. So that's good, but does the sun release light in other parts of the spectrum?
Yellow.
The whole darn thing, right? Because if we didn't get visible light from the sun, we would not be able to see. We would not be here. Wah, wah. You with me? Okay? So I want to show you a picture. You may want to draw this on a separate piece of paper, just in a little notes section. You don't have to be like super detailed on it, but I do want to show you this picture because I think it's important for you to see it. I don't know if you've seen a picture like this before. I don't know if this is something you guys do in chemistry or not. This is something we talk about a lot in physics. And we talk a lot about when we are looking at emission spectra or radiation curves for stars. Okay, so there are different kinds of stars that are out there. The type of light that is emitted by a star is dependent on temperature. So not every star is the same temperature. Okay.
Kinetic energy moving.
Boom, 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 right? Yeah, it all fits together. So this blue curve represents a star very similar to our sun. Okay? So if I was going to draw this picture on my notes, these are the things that I would draw. I'd probably draw an axis. Okay? I'm just kind of outlining what I would draw here. You don't have to include all of these wavelength things, but you could maybe put that wavelength is on this axis, and then you could write intensity on the y-axis, just so you have a kind of a sense of what's going on. Okay? And then these curves, I'm not going to test you on this, where's the maximum or whatever. But I just want you to be aware of this. That every single object that is not at absolute zero emits radiation. It emits light. Okay? I'm going to write that down. I want you to write that down too. Every object not at absolute zero emits radiation. And I don't want you to be afraid of that word. Again, another PR campaign, we've been taught that radiation is bad and scary and evil. But radiation just means light waves. That's all it is. Okay? Radiation is just light. So emits radiation or emits light. Some of it, radio waves don't though. And that's what we're going to get to right now. Okay? Every object not at absolute zero emits radiation. Okay? The wavelength or the frequency or the energy, because we just said a minute ago that those are all related, right? Depends on temperature. Okay, I'm kind of jumping ahead a little bit here, but for my chemist friends, you know that those molecules move back and forth and back and forth and back and forth, right? And molecules are made of charged particles. You with me there? Okay? And as charged particles move, guess what they make, friends? Light waves. Charged particles moving make light waves. That's what we're doing here. And so depending on how much they bounce back and forth and back and forth and back and forth, we're making light waves. Okay? And the bigger, the faster they move, the more energy they have, the higher frequency they have, the smaller wavelength they have. Okay? So we know that the sun emits light. We're glad that the sun emits light because we would not be here if it didn't. Okay? It emits some light over here in the ultraviolet. So this is the UV section. I would write down UV over here. Remember, UV is lower wavelength, right? They're smaller wavelengths. Okay? It emits some light in the visible part of the spectrum. And it emits some light in the IR part of the spectrum. Now, in fact, it actually emits some light that's further over here. These kind of go to zero, but if you zoom in, they come out a little bit. And same thing here, they're going to go out, right? So it goes infrared, it goes microwave, radio waves. You with me there? Okay. But as you can see in this first curve here, so I'm going to highlight this so you can see what I'm drawing here. Most of the light that the sun emits is in what part of the spectrum? The visible part of the spectrum, right? Which is good, because that's what we use to like function most of the time, right? But absolutely, there's a bunch of this UV stuff. So the sun gives off a bunch of UV light as well. That's the stuff that can hurt you, right? That's the stuff that can cause skin cancer if you don't protect yourself from it. Okay.
So
go ahead.
What does sunscreen do?
So sunscreen protects you from the radiation. Mm-hmm. So the way that UV light happens. I'll come back to this picture in just a second. Okay. So don't get upset if I'm jumping ahead too far for you. Okay. But ultraviolet waves, if you look at the picture, you see that the wavelength is getting smaller, right? Now the game is that as we move, the wavelength keeps getting smaller and smaller and smaller. And that means that it can get further and further and further into things. So your skin looks pretty solid to us. Why does it look solid to us? Because we're looking in the visible part of the spectrum. In the visible part of the spectrum, it is solid. But in the UV part of the spectrum, it isn't. There's spaces in between. And ultraviolet waves can get into our skin. They get into our skin, and then, oh my gosh, those UV waves, they happen to be oscillating at frequencies that are very similar to the natural frequency of your skin cells. And if they bump with the natural frequency of your skin cells, what are they going to do? They're going to monkey with it, aren't they? Yeah, they're going to burn it. They could cause genetic mutations, also known as cancer, right? That's what we're talking about. It's all just resonance, you guys. That's all it is, right? Like this all fits together. So UV, we absolutely use, or we all absolutely talk about it in terms of the sun. But again, it's not the only use, but it's the kind of like, it's the biggest one that we think about, Okay, and I'm going to write that down here just because it's kind of interesting to keep that in your brain. So the sun, so it's oscillating in the UV part of the spectrum. It has frequencies that equal the natural frequency of skin, which means resonance, right? Just like the microwave is at the natural frequency of water molecules. You with me there? Does this make sense? Like it's the same process that's happening. Okay? And it's not necessarily the skin cells. Like Oz would get mad at me if I actually said that. He'd be like, whatever. I mean, it's like the physics of it, but he would be like, it's not this, but it's like stuff in the skin cells. I don't remember any biology though. So like, I don't know how a skin cell mutates. Like, I don't know that. Go talk to him about that. But I know that there's some natural frequency stuff in the cells of skin that can be affected by these kind of waves. Okay, you with me there? Biophysicists figure this stuff out. Biology, physics, put it together, do good stuff, right? Question?
I remember learning about that in biology, like people closer to the equator, like skin that is better like, equipped with dealing.
Yep, you're exactly right. You're exactly right. All right, we got to keep cruising, friends. Holy cow, but I don't want to keep cruising yet. Oh my gosh, this is good. I love this conversation. Okay, so I want you to look here at what's going on. So this blue curve is at 6,000 K. What do you notice as these curves get, what's happening to the temperature?
Increasing.
It's going down. It's getting cooler and cooler and cooler. But do you notice that there's still emission, right? And that emission is also moving over further into the higher wavelength or the lower frequency waves. These curves are true for anything. Again, any object that's not at absolute zero emits radiation. Quick story, okay? Not something that any of you have experienced in person yet, but for those of my friends that have uteruses, you may experience this at some point, okay? You may become pregnant, and when you become pregnant, you get big. And one of the most awkward experiences that happens as you're walking around with this baby growing in your belly is that people are like, oh my gosh, look at you! And then they say, oh, you're just glowing. Which is like the most awkward thing. So don't ever say that to anybody, because really what that means is, wow, you have a really big belly, right? Like that's really what it means. You could be like, oh my gosh, I'm so excited for you. Like that's the thing to say, not you're glowing. So me as a physicist and a pregnant woman, people would say that to me and I'm like, you're right. I am glowing. I am glowing because I am not at absolute zero. Are you with me here? I am not at absolute zero, so I am emitting radiation. Now, I'm not emitting radiation in the visible part of the spectrum. What part of the spectrum am I emitting radiation in? The infrared part of the spectrum. I'm emitting radiation, but you are too, right? Now, I never actually said this to anybody because that's awkward. You don't want to like throw it in their face. But that's what I'm thinking. Like, I'm glowing and you're glowing. Like, yes, I have a baby in my belly. Like, I get that. But you know what I'm saying? So anyway, yes, I am glowing. Every pregnant woman is. But you all are as well. And if you weren't, that means that you're at absolute zero. So that's not good too. So the reason that I wanted to point that out was to come back here when one of you said that military uses the heat signature. All that is taking the glowing that you are giving off, right? You're giving off electromagnetic radiation in the infrared part of the spectrum, okay? It's very cool, like literally cool, because it's not hot.
Whoa.
Yeah? That's what we're talking about. All right, friends. Woo, that was a good day. Tomorrow's going to be great too, so come back. I'll see you then. Holy cow, I love this stuff. Yeah, I was shaking. Yeah.